Hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics, a TV channel. In my discussion today, I'm going to look at the concept of a classical adjoint of a square matrix. And this is going to be a follow-up discussion from the subsequent, or rather the previous videos which we had done on the concept of minus and cofactors. Now, to have us a reminder of our previous discussion, I basically mentioned that if we have a matrix given in terms of A, we can define what we refer to as the general element of this specific matrix A given in terms of this representation, whereby we are going to have A given as A, J given as such. So the I is going to be representing the specific, of course, row of this element, and the J is going to be representing what we refer to as a column. And therefore, we can have a general element of n of these elements of A given as such. Now, for a square matrix of this specific nature of elements, which are going to be consisting of 3 rows and columns, we're going to have this one given as a 3 by 3 size of a matrix for A. And therefore, we can represent various elements of A using these specific notations for the general representation, which we can give in this specific form, whereby we're going to have the various rows and columns being given by those or particular numbers which we can give for 1, 2, 1, 3 given as such, 2, 1, 2, 2, 2, 3, and of course 3, 1, 3, 2, 3, 2, and 3, 3 given as such. So each of these elements are going to be, of course, denoted using the ith row and jth column, which is going to be giving us the general case for what I've basically mentioned for A, I, and J given as such. So we introduced the concept of minus and cofactors, whereby we said that if we are going to have a general element of such a kind of nature for A, I, and J, we can find what we refer to as, sorry for that, minus of this specific element by deleting the ith row of such a kind of a matrix and the jth column. So if we delete one row and one column basically for a 3 by 3 matrix, then therefore we're going to have an n minus 1 by n minus 1 submatrix. And this implies that we're going to have a submatrix of a 2 by 2, which is going to be giving us what we refer to as, of course, a minus of these specific elements. Now, for us to find this minus, we're going to find the determinants of these submatrices. And therefore, if we have a matrix of this specific nature, just going to give this one using an example. Therefore, we are going to have 1, 2, 1, 3, 1, 0, 2, 1, 2, representing our A. So in this case, for us to find the minor of this specific, of course, element of 1 by 1 given as such, we're going to take this particular elements by deleting the ith row, which is going to be the first row, and the jth column, which is going to be the first column. And therefore, we're going to end up with this specific range of matrices, which can be given in terms of 1, 0. So this is going to be 1, 1, basically. So the remaining elements are going to be forming a submatrix of 2 by 2, which is going to be given in terms of 1, 0, and of course 1, 2. So for us to find the minus of this particular element, we're going to perform what we refer to as a determinant, finding the determinant, which is going to be, of course, finding this specific element of a diagonal, or the main element, the main diagonal elements, the product of the main diagonal elements, which is 1 times 2. And then this is going to be minus the product of the subsequent diagonal, which is going to be a diagonal running from the top right to the bottom left as such, which is 1 times 0 given as such. So this is going to be giving us a product of 2. So I've performed this specific operation for this kind of a matrix for various elements by deleting the respective row for this particular element and column. So for each of these specific rows and columns defined by these numbers, I'm just going to delete the respective, of course, row for the and the element, of course, column for this specific minor. For me to obtain this specific minor, for instance, if I take the second case, I'm going to delete the first row and of course the second column, and I'm going to obtain a submatrix of 3, 0, and 2, 2 given as such. So this is going to be 3, 0, and 2, 2 given as such. So there's the product of that specific, of course, diagonal elements and the difference between those main diagonal elements and of course the diagonal elements running from top right to bottom left are going to be giving me the determinant of that specific matrix. So each of these upper elements which are contained in such a kind of an arrangement is going to be performing some specific kind of a matrix, and therefore the elements are going to be arranged as such. Now we see that there's a relationship between these specific elements given in terms of A, I, and J given as such that we are going to have the product of this negative 1 raised to the I plus jth column, which is the sum of these specific two numbers, and then the multiplication of that one with the minus of this specific product which we have obtained from that one is going to be giving us what we call a matrix of cofactors. Matrix of cofactors, which are going to be given in this specific representation given as the ones which I've just given above. So in these specific evaluations, there is an element of negative 1 raised to the sum of this specific, of course, a representation for columns and rows. And these are going to be giving us what we refer to as a matrix of cofactors. So the above can give us what we refer to as the respective result from the above is going to be giving us what we refer to as matrix of cofactors, and we're going to have them given as this specific product which are going to be giving us. So the matrix of cofactors of A are given in terms of this specific representation. So I'm going to have 2 and of course negative 6 for the first row 1, and then I'm going to have negative 3 and then a 0 and then 3 given as such, and then I'm going to have negative 1, 3, negative 5 given as such. So this is going to be forming what we call a matrix of the cofactors which I've just given on the board, and we're going to consider using this matrix of the cofactors from a previous relationship. We have looked at the concept of course inverses. It is in trying to of course try to define what a classical adjoint is. So let me just have this one done. So we have seen the procedure for obtaining the matrices of the cofactors from this particular representation which I've just given on the board. Just going to reserve the one from the right side for our particular evaluation. So we can define a classical adjoint of a square matrix such as A, which is denoted as a classical adjoint. So this is going to be just a summary definition of the classical adjoint. So a classical adjoint of a square matrix such as A is denoted using this specific, of course, denotation. We are going to have A dj A given as such is the transpose of the matrix of cofactors of this specific matrix of A. So this one, of course, we have obtained the matrix of cofactors, which of course I've just shown from my previous statements, and therefore we can define a classical adjoint of a square matrix using the this specific notation which I've just shown on the board, which basically is a transpose of the matrix of cofactors. So I've introduced a new term which we are going to look at in this specific case. So suppose we have a matrix of the form A given in this specific order 2, 1, 3, 1, 0, 2, 1, 2. So a transpose of this specific matrix is given as A T given as such. And this is defined by forming the rows are going to be forming columns. So we're going to have the first, of course, or the columns are going to be forming rows in a sense that we're going to have the first column of 1, 3, 2 given in terms of a row. And of course, we're going to have the second one, 2, 1, 1, and the third one, 1, 0, 2. So basically what I've performed in this, I'm going to make the columns being rows, or the rows being columns. And in this case, this is going to be forming what we refer to as a transpose. So if you consider the matrix of cofactor, which we have given in this specific case for the general case for our representation for A, we're going to have A given in terms of this specific factor. And of course, a generation of the matrix of the cofactor, which is going to be given in terms of, so the matrix of cofactors, which is given in terms of 2, negative 6, 1, negative 3, 0, 3, and of course, negative 1, 3, and negative 5 given as such. we're going to have a transpose of this specific matrix by having it given in terms of the, so the columns are going to be forming rows, and we're going to have it as 2, -3, -1, -6 is 0, of course 3, and then we're going to have 1, 3, -5 given as such. So this is going to be forming what we call a transpose of the matrix of cofactors, which are going to be forming what we refer to as the classical adjoint. So this is going to be denoted using this specific, of course, notation which I've just given on the board. And we're going to see that we can find the matrix of the cofactors and, of course, this is specific representation for the transpose of that particular matrix. And in our previous video, so therefore we are going to see that we can, of course, define the classical adjoint from this specific concept. Now I'm going to use this specific classical adjoint from my previous discussion so that we can find a relationship between this classical adjoint and other specific concepts which we are going to come across. So I'm going to reserve this specific matrix of the cofactor and the matrix of or the classical adjoint and this specific matrix of A given as such. Perhaps I can just write it on the top right corner of my board. So let's remind ourselves that basically this is going to be a transpose of the matrix of cofactors given in terms of an adjoint. So this is going to be -1, 3, -5 given as such. I hope I've just written them correctly. So this is going to be an adjoint of a matrix over A given as such. So let's explore the relationship between this specific adjoint and the other factors which we have learned from our previous discussion. Now in our discussion on the concept of what we refer to as the inverse of a square matrix, we had said that we are going to have a various range of properties which we are going to define for particularly the properties of inverses of matrices. So we said that if we have a matrix, a square matrix over A, which is invertible, so we had talked about the concept of an inverse of a matrix A. So if a matrix A is said to be invertible, then there's going to be another matrix in a way that if we have the product of A times B or B times A, so this is going to be a commutative property. This is going to be giving us what we refer to as identity. So in a sense, we're going to say that B is going to be performing a specific, or B is going to be such a matrix that it's going to be unique and it's going to be the inverse over A. So in a sense that if we have this specific matrix which is going to be defined as A, and of course we are going to have what we refer to as the inverse of a matrix given as A. So the product between the two, which is going to be having a commutative property, is going to give us a result of what we refer to as identity. And remember from our previous discussion on the concept of identity matrix from what we refer to as an n number of values, which is in our case n is equivalent to 2. So basically this is going to be a 2 by 2 identity matrix. And in case if we have n equivalent to 3, then therefore we are going to have this a specific matrix in terms of an identity given as such. So we are going to consider these two specific factors and try to, of course, find the relationship between the classical adjoint and some of the concept like inverse, which I've just defined using this specific example. So we are going to look at this from this particular perspective. So list of various properties which we had defined from our previous case, we had said that this can be given in terms of the inverse of A, which is going to be giving us identity. Now, this specific property, I've just used it to denote what we refer to as the concept of inverse from my previous statement. So if we have an inverse over A given as such, and we perform a transpose of that specific inverse, this is going to be giving us A transpose the inverse of that one, given as such. And of course, we're going to see that among others, perhaps I can list the third one. This is going to be, of course, the determinant of a matrix is given as 1 all over the inverse of A given as such. So we're going to use such a kind of properties in trying to define the concept of or try to see one of the applications of this concept of a classical adjoint, whereby we are going to have the classical adjoint given in terms of this specific, of course, representation. Thus, if we're going to have this specific matrix of the determinant not equivalent to 0, then we can have the inverse of a matrix defined by having it as the ratio between the determinant of matrix and the classical adjoint of A given as such. So in this case, we can find each and of course the subject of we can make each of these either the inverse, the determinant, or the classical adjoint the inverse of course, or the square, or the subject of the formula for these various aspects, whereby we're going to see that we can have a general case of A times the adjoint over A, of course, is going to be giving us the product of what we refer to as the determinant of A times A times the inverse of A, where the two as I said is going to be forming what we refer to as identity. So therefore, we can explore this specific relationship and see what this specific adjoint holds for us in trying to find various aspects of the determinant, perhaps, and the inverse or identity of thus a specific matrix. So we're going to consider a specific case of a matrix, whereby we're going to have a matrix represented by this specific case for a matrix of A given as such, and a classical adjoint. So we're going to use this relationship whereby we have said that if we have a matrix represented as this specific aspect, so sorry for that. So if we have a matrix represented this specific relationship over A, the classical adjoint over A is equivalent to the, of course, identity of that specific matrix and the determinant. So let's look at a case whereby we have A and the classical adjoint given us the two of these. Let's see whether it's going to be giving us the determinant and identity given as such. So we will have this one given in this specific case for the adjoint of this matrix, which is going to be 2, -3, -1, -6, 0, 3. And we're going to have this one as 1, 3, -5. So let's have this specific adjoint multiplied by the, of course, 1, 3, 2, 2, 1, 1, and 1, 0, 2 given as such. So this is going to be the adjoint of A times A. So the 4 times the matrix of A. So in this case, I'm finding the range of values of -9, 0, 0, 0, -9, 0. So limit to this one. And then we're going to have 0, 0, -9 given as such. And if I do this one by having the matrix of A given as such, which is 1, 2, 1, 3, 1, 0, 2, 1, 2, times the adjoint, which is 2, -3, -1, -6, 0, 3, 1, 3, -5. So still I'm going to obtain, so this is going to be A and the adjoint. So I've just interchanged this one to check for the properties of our commutative. I'm going to have -9, 0, 0, and 0, -9, 0, 0, 0, -9. So if you try to look at this one, we had talked about the concept of a multiplication of matrices times the scalar, of course, quantity. We're going to see that we can have this one, of course, as represented in terms of identity times a specific matrix, which is going to be forming what we refer to as our, of course, determinants. So therefore, I'm going to do away with this. So the two matrices which we have obtained as a product can be given in terms of -9 times 1, 0, 0, 0, 1, 0, 0, 0, 1. And the second case as well is going to be giving us -9, 1, 0, 0, 0, 1, 0, 0, 0, 1. So basically implying that we are going to have this specific value which is going to represent the, of course, a determinant, and the next values are going to be representing identity for changing of this specific position of our adjoint and A given as such. So we're going to see that this specific formula which we have given above at the board is basically true, and therefore using this relationship we can either obtain what we refer to as a determinant or the other values which we are going to give in terms of identity, or the classical adjoint in a sense, which is going to be giving us the above relationship which I've just basically mentioned. So therefore, we are going to see that generally this is going to be always the case for any kind of matrix which is going to be represented as a square matrix of a particular matrix of course, over A, which we have said. Therefore, times A is equivalent to the adjoint over A